plus mathematical intelligence layer. Why mathematics? 20 mathematical domains, summary, power summary and about Dr. Pradeep K. Suri. Why mathematics in Brain NeuroGov Plus? Mathematics is one of the fundamental hidden foundations of Brain NeuroGov Plus. Artificial intelligence can process language and information, but enterprise intelligence also requires measurement, comparison, probability, optimization, prediction, risk calculation, evidence evaluation, and decision modeling. Mathematics provides the formal language through which these activities can be represented. The mathematical layer should therefore be understood as a conceptual intelligence layer, not as a claim that every formula shown has already been implemented in every NeuroGov Plus engine. The purpose of this register is to identify the mathematical domains that can support the architecture and provide a framework for mapping them to the engines. 20 mathematical domains. 1. Arithmetic, the numerical foundation. Arithmetic provides the basic operations required by virtually every enterprise intelligence system: addition, subtraction, multiplication, division, percentages, and numerical comparisons. It forms the lowest mathematical foundation for financial calculations, quantities, measurements, KPIs and operational metrics. Representative formulas. A plus B, AB, A times B, A/B. Purpose: convert raw numerical information into measurable values. Remark: foundational mathematics used throughout computational systems. 2. Algebra, relationships and variables. Algebra allows Brain NeuroGov Plus to represent relationships between variables rather than treating every calculation as an isolated number. Equations can represent business rules, relationships, constraints, and analytical models. Representative formula. X plus B equals 0. Purpose: express and solve relationships between enterprise variables. Remark: a fundamental mathematical language for analytical intelligence. 3. Linear algebra, multidimensional intelligence. Linear algebra is particularly important for AI because enterprise information can be represented as vectors and matrices. It provides mathematical mechanisms for transformations, feature representations, and multidimensional computation. Representative formula. Y equals X. Purpose: represent and transform multidimensional information. Remark: highly relevant to machine learning and AI computation. 4. Calculus, understanding change. Calculus provides methods for understanding change. In an enterprise environment, change can represent changing costs, demand, production, risk, performance, or system behavior. Representative concepts. dx dy, indefinite integral f, x, dx. Purpose: measure rates of change and accumulated quantities. Remark: particularly important for optimization and dynamic modeling. 5. Probability, managing uncertainty. Enterprise decisions rarely operate with complete certainty. Probability provides a formal mechanism for representing uncertainty and estimating the likelihood of events. Representative formula. P. A. Purpose: quantify uncertainty and likelihood. Remark: important foundation for risk and decision intelligence. 6. Statistics, converting data into evidence. Statistics transforms collections of observations into meaningful information through measures such as mean, variance, standard deviation, and distributions. Representative formula. X equals N1, I equals 1 sigma Z. Purpose: summarize and understand enterprise data sets. Remark: central to analytics, monitoring, and performance intelligence. 7. Bayesian mathematics, learning from evidence. Bayesian mathematics provides a mechanism for updating the probability of a hypothesis when new evidence becomes available. Representative formula. P, AB, equals P, B, P, BA, P, A. Purpose: update conclusions as new evidence arrives. Remark: potentially valuable for evidence-driven reasoning and decision intelligence. 8. Optimization, finding better decisions. Optimization mathematically expresses the search for the best possible outcome subject to objectives and constraints. Representative form. SMINF, X. Purpose, find the most effective solution among alternatives. Remark, highly relevant to resource allocation, planning, and decision intelligence. 9. Graph theory understanding relationships. Graph theory represents entities and their relationships as nodes and edges. This provides a mathematical foundation for understanding enterprise networks, knowledge relationships, and dependencies. Representative form. G equals VE. Purpose, model relationships among enterprise entities. Remark, strongly relevant to knowledge graphs and network intelligence. 10. Information theory measuring information. Information theory provides mathematical mechanisms for understanding information, uncertainty, and entropy. Representative formula. H, X, equals X sigma P, X, log, X. Purpose, quantify information and uncertainty. Remark, relevant to information retrieval, AI, and knowledge processing. 11. Logic and Boolean mathematics governance rules. Logic provides formal mechanisms for expressing conditions, implications, and decisions. Representative forms. AB, AB, A. Purpose, represent rules and logical conditions. Remark, particularly relevant to policy, governance, and compliance mechanisms. 12. Geometry spatial intelligence. Geometry provides mathematical methods for understanding distance, position, shape, and spatial relationships. Representative formula. D equals x2 x1, 2 plus, y2 y1, 2. Purpose, analyze spatial relationships and measurements. Remark, potentially useful for physical assets, locations, and multidimensional intelligence. 13. Time series mathematics understanding enterprise movement. Enterprise intelligence is not only about the current value, it is also about how that value changes over time. Representative form. YT equals F, YT1 YT2. Purpose, understand trends, cycles and temporal behavior. Remark, important for forecasting and management intelligence. 14. Risk mathematics quantifying exposure. Risk mathematics connects probability with potential impact. Representative conceptual formula. Risk equals P, event, times impact. Purpose, quantify potential exposure. Remark, a useful conceptual foundation for governed enterprise decision-making. Exact NeuroGov plus implementation should be formally defined. 15. Financial mathematics enterprise financial intelligence. Financial mathematics provides mechanisms for modeling growth, present value, future value, ratios, and financial movement. Representative formula. FV equals PV, 1 plus R, N. Purpose, support financial analysis and modeling. Remark, particularly relevant to financial and management intelligence. 16. Machine learning mathematics learning from data. Machine learning relies heavily on mathematical functions that map inputs to outputs and optimize model parameters. Representative form. Y caret equals F theta, X. Purpose, represent learned relationships between inputs and predictions. Remark, mathematical foundation of many AI learning systems. 17. Neural network mathematics cognitive computation. Neural networks use mathematical transformations across layers to convert input representations into increasingly complex representations. Representative form. Z equals WX plus BA equals sigma, Z. Purpose, transform information through computational layers. Remark, relevant to the AI cognitive processing layer. 18. Similarity mathematics finding relevant knowledge. Similarity mathematics allows information objects to be compared mathematically. Vector similarity is particularly relevant to retrieval and knowledge systems. Representative formula. Cos equals XY XY. Purpose, Measure similarity between information representations. Remark, highly relevant conceptually to RAG and semantic retrieval. 19. Decision mathematics from analysis to action. Decision mathematics combines evidence, probability, utility, constraints, and alternatives to evaluate possible decisions. Representative form. EU, A, equals S sigma P, SA, U, SA. Purpose, evaluate alternatives under uncertainty. Remark, directly aligned with the concept of enterprise decision intelligence. 20. Composite intelligence mathematics integrating the enterprise. The highest conceptual level is the integration of multiple mathematical dimensions into a governed decision process. Conceptual NeuroGov plus formulation. Decision equals F, data knowledge context risk policy. Purpose, integrate data, knowledge, context, risk, and governance into enterprise decision intelligence. Remark, this is a conceptual NeuroGov plus formulation, not an established mathematical law. It should be formally specified and validated before being presented as an implemented mathematical model. Summary. The mathematical layer of Brain NeuroGov Plus can be viewed as a multi-domain mathematical foundation supporting enterprise intelligence. It can connect data rightward arrow measurement rightward arrow statistics rightward arrow probability rightward arrow analysis rightward arrow prediction rightward arrow optimization rightward arrow risk rightward arrow governance rightward arrow decision. The mathematics does not replace the AI model. Instead, it can provide the formal computational structure around the AI model. This distinction is important. The AI model can generate cognitive representations. Mathematics can provide measurement, formalization, validation, optimization, and decision structures around those representations. The 20 domains above are therefore a working mathematical taxonomy for Brain NeuroGov Plus, not yet a claim that exactly 20 mathematical branches are implemented in the current product. Power summary. Brain NeuroGov Plus mathematics equals governed mathematical intelligence. Brain NeuroGov Plus can be conceptualized as bringing together data, downward arrow, knowledge, downward arrow, mathematics, downward arrow, cognitive intelligence, downward arrow, analysis, downward arrow, risk and governance, downward arrow, decision intelligence, downward arrow, enterprise action. The mathematical layer provides the ability to measure, calculate, compare, model, predict, optimize, quantify uncertainty and evaluate decisions. This makes mathematics more than a supporting utility. It can become a formal computational foundation underneath enterprise intelligence. The central idea. Mathematics gives Brain NeuroGov Plus the ability to turn enterprise information into measurable, analyzable, optimizable, and governable intelligence. About Dr. Pradeep K. Suri. Dr. Pradeep K. Suri is the inventor and architect of Brain NeuroGov Plus, an enterprise artificial intelligence architecture focused on governed enterprise intelligence. Brain NeuroGov Plus is conceived as a model-independent enterprise intelligence architecture, bringing together AI governance, AI memory, cognitive reasoning, decision intelligence, responsible AI, and specialized enterprise intelligence engines. Within this architecture, mathematics can provide an important foundational layer, a formal language for measurement, analysis, probability, optimization, risk, prediction, and decision-making. The mathematical intelligence layer therefore represents a further development of the broader NeuroGov Plus vision. 1. Brain Endomains and GPTs. With mathematics contributing the formal computational foundation through which enterprise intelligence can be measured, reasoned about and governed. Dr. Pradeep K. Suri. Inventor and architect Brain NeuroGov Plus.